Welcome AP Stats students. Today we're going to take a look at problem set 4.1b. Couldn't do it in class because of the test. So our first problem is 4.17. And taking a look. Okay. Topic is exact exponential growth. Buy a bond worth $500 and it gets interest at 7.5% each year. So it is perfectly exponential. So part A, let's find the value of the bond at the end of 1 year all the way out to 10 years. So quick, easy way to do that. First of all, you're going to want to come up with the equation. You might recall this equation from a past math class. Amount of an investment is equal to the principal multiplied by 1 plus the rate raised to the number of years, right? This is for compound interest, annual. So in this case, it is an annual investment. We have 500 is our principal and our interest rate 7.5%. So cleaning it up, I get 500 times 1.075 raised to the number of years. Of course, with my calculator, I'm going to use y and x. And the easy thing to do would be just type in 1 through 10 years in list 1 and then throw your formula into list 2. Okay, and there we go. When I hit enter, I will get the values of the investment for each year all the way out to year 10. Easy peasy. Okay, part B, they want me to make a scatter plot. So list 1, list 2, usual stuff. And there's my scatter plot. Again, don't forget to label this if it's a test question. People keep forgetting to label your X and Y axes and put a title on it if it's a test question. All right, they want me to connect the points with a smooth curve. Obviously, if it's on your paper, just draw the curve in. If you want to do it on the calculator, type in your equation. And then when you graph that, you get a nice curve. And again, it's perfect exponential, so the line goes through every point. Realize, however, if this is an annual investment, you actually can't take it out part way into a year and get part of the interest. CDs and some certain investments, you're required to go for the full term in order to get the growth for the year. All right, part C, let's take the logarithm of each of the y values. Okay, so that's again pretty simple. Find an empty list. Log. There's my wonderful dog. Take the log of list 2. And there you go. And if we are correct, right, if this was exponential, which it was, obviously, we defined it to be perfect exponential growth, you'll see that these values here are now growing by a fixed amount. We add the same amount each time, right, because the x values went up by a fixed amount. And so now it should be perfectly linear because, again, logs are the inverses of exponentials. So now let's graph list 1, list 3. And there you go. Sure enough, we now have a perfectly straight line because we started with a perfect exponential curve and we took the log, which is the inverse, and so now I have perfectly linear. And there you go. That was 4.17. All right, on to 4.18. More with exact exponential growth. All right, this time we have Alice, right, is sticking with her 7.5 annual interest rate. Fred, however, he's going to start with $500, and instead of investing it, he's just going to save, and he's going to add $100 each year, but he's just sticking it under his mattress, not getting any interest on it. Okay, so let's take a look and compare these two investments. Okay, and it's just to go out 25 years. Okay. Well, we already have Alice's in our calculator, right? Okay, that's right there. That's Alice. Now Fred apparently doesn't trust institutions to invest with, so he's just going to start with $500. I'll use Y. He's going to start with $500, and then he's going to add $100 every year. Okay, so we're going to compare these two equations. Okay, so there's Alice's equation. Let's go to Fred. And I'm actually going to go ahead and, just to get a decent viewing window for starters, I'm going to go back to Alice's data. So 9. So there's Alice for the first 10 years. And let's compare that to Fred for the first 10 years. All right, there's Fred for the first 10. So looks like, hey, Fred's doing great. He's outperforming Alice, right? But this is after 10 years. Let's take a look at changing this window a bit. We want to actually carry it out to, it says 25 years. So I'll make that 26. It's always good to go a little bit past. May as well make that 1. Let's see, my maximum 25 years, I'll just guess. Let's go for $5,000. See what happens. Okay, so again, there's Alice. So you can see what happens somewhere over here, right? That linear growth, it stays nice and straight. But that exponential growth, it's curving, it's concave up. So it keeps accelerating and accelerating and accelerating. And somewhere over here, Alice actually passes Fred, right? Her investment actually makes her more money, even though she only put $500 in, and that was it. She never added any more money, okay? So let's see, after 25 years, who's gonna have more money? Let's take a look. Fred, 25 years in. Fred will have $3,000 after 25 years, right? Let's try Alice's after 25 years. Okay, that one I can't do in my head. So this is the multiplier. She's going to multiply her initial investment by a little over 6. Because that interest has compounded. And sure enough, she has overtaken Fred. So somewhere probably around year 24, she's going to catch Fred. So you can see by year 25, Alice has actually surpassed Fred. And she never had to add any money. She just let the interest do the work for her. That's the moral of the story, by the way, for investing. You want to start early. The sooner you start, the more years you can let that compound interest do the work for you. All right, let's move on. Question 19. Let's see, question 19. Fish in Finland. Everyone's favorite thing to do, go fishing in Finland. All right, we're gonna make scatter plot. So let's put the data in the calculator. What are we plotting? Length, okay. Okay, and we wanted to scatter plot weight against length. So length is actually my explanatory variable. So this is one of those problems where I just, put the data in and then I read and it's like, oops. So list 2 is actually going to be my explanatory variable here, but that's fine. Okay. Oh, go ahead and turn that, get rid of those other equations. You can see they're slowing my calculator down. It's trying to graph them all. There we go. All right, so there's my scatter plot. Length is explanatory and weight is response. Again, make sure you're labeling those X and Y axes. And then let's see, describe the pattern that you see. Well, if it had just been a little bit of this, I'd say, oh yeah, it looks linear, but right, with the points over here on the left, I'm going to say this looks curved. It looks to be a concave up curved relationship. Okay, part B. How do we expect the weight of animals of the same species to change as their length increases? Okay, well, think about weight and think about length, right? Length is governed by one dimension, right? But weight will increase based on total size, right? It's more like a volume thing. So as my length is increasing, I bet my other dimensions are also increasing, and all of those increasing together will of course affect the weight. So weight is much more of like a three-dimensional measurement, whereas length is a one-dimensional measurement. So that's what I'm seeing. I would think that it's going to be something along the lines of a cubic, right? So let's see, make a transformation of weight. That should straighten the plot if I am correct. Okay, so if I am correct, I think it is roughly a cubic, so that is not exponential. I'm not covering cubic regression, so what I'm going to do is use my kind of jack of all trades, the power relationship, because it can approximate a cubic. So to do that, I want to log both variables. Okay, so let's log list 1. Let's log list 2. Now, and again, remember I have these reversed, so I'm now going to graph list 4, list 3. And there we go. So sure enough, when I logged both the X and the Y, I got something that looks pretty linear. So my idea that this is a cubic is somewhat reasonable, right? Because now I can see a nice linear relationship in my log-to-log data. Okay. All right, moving on. More with fish. All right, plot the widths of the 12 perch in the previous problem against length. Okay, so here we're going to do width and length. I already luckily have the length in there. So let's get the widths. Okay, so I now have the widths in there, and we are plotting width against length. So again, length is going to be my explanatory, and width will be my response. So now list 2 is x, list 3 is y. Okay, so there we go, length and width. What do I see? This one looks pretty linear. And that makes perfect sense, right? They're both one-dimensional measurements, so as the fish grows in length, it should grow proportionally in width. So not a surprise at all to see a fairly linear plot there. Okay, moving on. Next problem, mold, everyone's favorite, right? All right, you can read all about mold data. Let's graph the mean colony size against time. Then graph the logarithm of the mean colony size against time. Okay. So, enter the data. And we can ignore the middle values because it said just the mean. Okay, and we're ready to graph. For some reason, my axis is really wide, but that's fine. The key thing here is, what do I see? I see concave up. So I'm going to conclude that linear would not be the best choice for that data set. Okay, so now let's graph the log of the mean colony size. So log of list 2. Okay, now this is interesting. Okay, on the surface, when we first saw the problem, we saw something that was concave up. It looked like, exponential would fit it pretty nicely. But here, once I take the log, I see things that aren't quite smooth, right? There's a little bit more to this than just a clean exponential relationship, okay? And here we go. Microbiologists say that there are 3 phases in the growth rate of these colonies. Okay, and that would explain why I'm seeing kind of one here, and then somewhere up here it looks like it slows down again. So that makes sense. Briefly describe the 3 phases, making specific references. Okay, so there you go. So the beginning phase is fairly, as you can see, it's fairly constant. I don't really see much growth at all for the first 6 hours or so, right? Then in the middle phase, right, I can see this is where it takes off and it starts to really grow pretty quickly. And then right there at the end, it tails off again. So those appear to be the 3 phases. Okay, no growth at all, just constant. Then I would say through here, right, it's the log. The log has done a good job of making it look linear, so I'm going to say it's probably exponential through here, and then it tails off at the end. I wish I had more data over here to try to come up with a better guess as to, does it go back and revert to linear? Does it continue to grow exponentially but at a slower rate? or is it something else? Okay, let's see. It looks like exponential phase is from 6 to 24 hours, just like we noted here, right? There's the 24-hour mark, there to there. Let's find the least squares regression line of the logarithms of the mean size for only the data 6 to 24 hours. Okay, so we're going to have to delete some values here. So we want to delete the first two. And then we want to delete the last one. Okay, now, there it is, the 6 to 24 hours. Well, this is the log, right? And it looks pretty linear, so I like it. All right, so now we're going to do regression on that. There we go. Moderately strong positive correlation there. And we're going to use this line to predict the size of a colony after 10 hours. So realize this is in terms of log. If you'd like to, you can transform it to get it back in terms of regular colony size when it hurts. So that's what I'm going to do. I'll define this equation to be 10 raised to the y sub 1. And now I can use that in terms of the original data without having to worry about logging anything. Okay, so there's my prediction for, oh, I must have messed up, let me see. 10 hours, yeah, that's way too high. Let's take a look, see if we can figure out what how I messed this up. Make sure I have my data correct. 6 through 24, yes. 6, yep. Let's make sure this is the log of list 2 again. Okay, and let's do linear regression on that. Oh, there you go. I didn't use list 3. And that's one thing you're going to do. From time to time, you're going to make a mistake, and that's perfectly fine. I'm kind of glad I made this mistake because you could learn from it. So I forgot to change that to list 3. I got an equation, and I looked at my prediction, and it didn't make sense based on my correlation and based on my eye, right, telling me how accurate the prediction should be. It was just off by way too much. So I knew something went wrong. I retraced my steps, and I found my problem. I had left that as list 2. Needed to change it to list 3. So do it over. Oh, there we go. Yeah, the correlation of 0.85, this is much, much stronger. So this makes good sense. All right. And that should be in there. Good. So let's try this again. At 10 hours, I'm predicting 1.8, and that's much more reasonable. Okay. All right, moving forward. Question 22. We're going to look at trees. Most exciting thing we could study, right? Trees. This one's actually real nice in that they didn't give you all that data and make you punch it in your calculator. It's very tedious. Instead, they handed you the equation, so that's nice. Notice that this is in log, right? Log. So they're doing a power transformation on it. So we want to take that log data and translate it into a power model. So just a little bit of algebra there. Okay, so I'll start by writing down the given equation. Notice it's log base e, also known as natural log, so you should be familiar with that notation, natural log of y. Okay, so basically they're asking us to solve for y. Remember, natural log is base e, maybe that's why they wrote it the way they did. So convert this to exponential notation. So the base again is e. Okay, now use properties of logarithms, or not logarithms, sorry, exponents first. So if I'm adding exponents, that means I must have been multiplying with the same base. And I'm going to rearrange that. Okay, right. I rearranged that because I know that e to the natural log, right? Those are the same base, right? So we have a property for that. I know that that's gonna just cancel out, so I can think of it like this. Right, think of it like that. So this just becomes x to the 2.42 power. And you can work out e to the -2 if you want. I mean, that's fine. Use your calculator. But I think this was kind of the point of the question here, was just to get to a power equation that's reasonably nice to work with. So I would just leave it like that if it were me. All right. Let's see. Part B to that. Let's use our equation and estimate the biomass of a tree that's 30 centimeters in diameter. Okay. So let's see, 30 raised to the 2.42 power, and that's going to get multiplied by, here's my e to the x. Oh, e to the x is down here. And there we go, 508. All right, that's fun stuff. Next problem, we're going to go back and look at our mold some more. This has been a very interesting problem set, right? Studying mold, trees, and fish. Real exciting data. All right, so we're going to go back. Find the correlation between log and mean size. 6 to 24. Make a scatter plot of the logarithm of individual size measurements against hour. Oh, individual size measurements against hours. Okay, so I believe we already did the beginning, the correlation between log of the mean size and hours. Didn't write it down. We'll write it down now. Luckily, I still have that data in the calculator, I believe. Yep, so we still have it. So let's find the correlation for using lists 1 and 3. Okay, so there's my correlation, about 0.99. So this is using the mean. Okay, now we got to enter all of the data instead of just the means. Yay, isn't that fun? So let's go back. So we're going to have 3 entries for 6, 3 entries for 9, so on and so forth. So. Oops, and now put in our data. Yay, wasn't that fun watching me enter numbers in a calculator? Okay, so now we have all the data in there instead of just the means. And the question is, we're going to make a scatter plot of logs of that. So let's log it. And scatter plot, list 1, list 3, looking good still, okay. And there we go. Got a bunch of equations in there. So there we go. Now, this is the case when I have the actual data, right? I'm going to have a stack of points because I had 3 points for each time. So that's why I have these little stacks. And of course, since I have these stacks, that means I have more variation. So I am expecting a weaker correlation. I assume that's what the point of this problem is. Find the correlation, yeah. And sure enough, there's the correlation. And yes, indeed, it is weaker. And it's not surprising at all because, again, we see more variation with individual data as opposed to the mean of a data set. All right, one more question and we'll be done. This one looks a little more exciting. Who doesn't want to be like Galileo Galilei? So we have some data. And we're talking about basically rolling an object and letting gravity take over. So I'm expecting right out of the gates, right? This is should be a quadratic, right? Objects falling due to gravity, right? Those are parabolas. So let's enter our data and we're going to plot distance against height. So again, distance is y, height is x. So I'm just going to go ahead and, when I enter it in the calculator, put height in the x. I missed a point in there. Okay, so there we go. And let's make our plot. I'll clear that equation and, oh, forgot my zoom. there we go. Well, that's an interesting plot. Make sure I didn't misenter that coordinate. I sure did. See, it should be 1,000. And again, mistakes are going to happen, right? If you're paying attention, you're going to go, wait a minute, something doesn't look right. And then you're going to do exactly what I just did. You'll catch your mistake. You'll fix it. And now that looks a lot better. Okay. All right, so letter A. Think before you calculate. What power will tend to straighten the graph? Well, actually, I already figured that one out in that I'm thinking that this is governed by a quadratic, right? I think it's gravity, which is a parabola, quadratic. So I would be thinking, right, the inverse of a quadratic would be a square root. So I'm thinking a power of roughly 1/2 should help to fix this, straighten it. All right, B, move along the ladder of transformations in the directions you've chosen. What transformation do you suggest? Okay, so let's basically transform the data. So since I think it's quadratic, and again, we don't do quadratic regression, right? So I'm thinking it's kind of a parabola, and we're only seeing a little bit of it. Let me just double check that I do have all the data in there correctly. Yep. So we don't have quadratic as a choice. Well, we do, but I haven't taught you that. So it's the power. That's what we're using for all of these non-exponential curves, right? It's our jack of all trades. So to do that, we need to take the log of both lists, both variables. Okay, and now we're going to do regression on list 3, list 4. Let's graph it too, just to take a peek. Okay, so looks fairly linear. Let's take a look at what happens when we perform regression on that. And we do get a pretty nice correlation there. Okay. And also notice the B value there, right? That B value is your power, right? So the power we got is just a little bit above 1/2. So that's kind of what we were thinking it should be, because if this is indeed a quadratic, a square root would be the way to transform it and make it linear. And sure enough, we got something that's almost a square root, right? 0.5 is an exact square root. So we got a power that is right in line with what we were expecting to get. Okay. Oh, yeah, we already graphed it. And there it is with the equation. Okay. It doesn't say, but if you wanted to, you could now back transform that and turn it into a power equation, just for fun. All right, so there's our problem set. Hopefully it made sense, and hopefully you did well on your test.